So this is where we apply the elastic curve equation. Okay. So from here, after applying the elastic curve equation, we are going to integrate the third time. After applying the applying the elastic curve equation, we are going to apply EI. Now this is dy by dx. And dy by dx, if you look at this expression over here, right, the slope dy, so the change in y, so this is our dy. And over here in the x direction, this is our dx, right? So dy by dx is also equal to ei theta. And this will be equal to, we're now going to integrate minus omega naught x cubed over 6L plus by C1x plus by C2. This is dx. Okay. So what we have over here is equal to minus omega naught x4 over 24L plus by C1x squared over 2 plus by C2x plus by C3. And then finally, when we're going to integrate the third time and the fourth time, we're going to have the expression y or EIY is equal, so we're going to integrate minus omega naught x4 over 24L plus by C1 x squared over 2 plus by C2x plus by C3, and the whole thing dx. And this whole expression will now become minus omega naught x5 over 120L plus by C1 x cubed over 6 plus by C2 x squared over 2 plus by C3x plus by C4. Okay. So this over here can be used to determine deflection of the structure. And you can see we have how many unknowns. If I were to highlight the unknowns, we have one unknown, C1, wrong color, sorry. We know that we have C1, C2, C3, C4, and we have how many boundary condition? 1, 2, 3, 4. So we can determine C1, C2, C3, and C4. So this is how you apply the elastic curve theory to determine the deflection. So at the end of the day, this expression over here, okay, this expression over here, or this expression over here, okay, is basically trying to determine, deflection of the what? Of the beam. So if this is our, I mean, this is still our beam. If I put two axes down here, okay, if I put two axes down here, right? So the expression, the deflection of the beam, right, basically is this expression over here. So I'm going to copy this expression. Bring it up here, right? And I'm going to clear this off. This is the expression, right? Right, this curve over here. So this is our x, and this is our y, and this is y as a function of x is equal to 1 over EI, square bracket, the whole thing. Okay. So that's how you determine the deflection of the beam. Okay. So now, coming back to our buckling problem. Okay, so now we come back to our buckling problem. So we know from our buckling problem, where were we? We were at this point over here. Okay, so I'm going to copy this entire expression over here or entire diagram. You don't need to do this, okay? Right. So now we know why this expression, okay? How to apply this elastic curve. So now we are going to apply the elastic curve, right? So now we are going to write an expression where we have EI is d squared y over dx squared. And this whole thing will be equal to moment at point Q. Let me recall where's point Q. Point Q is at this point over here, okay, where we are trying to find our y. So now, if we were to rearrange the expression, we have d squared y over dx squared. This will be equal to moment about point Q over EI. And we know that moment about point Q will be equal to, let me write properly, not MQ, moment about point Q. Okay. And we know that moment about point Q is equal to minus PY over what? EI. Okay. Minus PY over EI. And we know this, right? Moment about point Q is minus PY. Okay. So from here, we can write this out to be d squared y over dx squared plus by big PY over EI, the whole thing is equal to 0. Okay. I forgot which equation we are on now. Let me check. I really forget. Yeah, I think it was 5 or 6. It's okay. I'm going to start from 1 again. Okay, so we are looking through here. We know that you're looking at equation. So we know that equation, oh, okay, I'm going to use A. Equation A is known as a homogeneous second order differential equation. Okay, we know that. So what we're going to do next, I'm going to let small p. This is different, yeah. The previous one is capital P. Small p is equal to square root of big P over EI. Okay. Right? I'm going to let small p is equal to big P over EI, the whole thing, square root. Okay. So therefore, equation A, okay, therefore equation A becomes d squared y over dx squared, right? Plus small p squared multiplied by y, the whole thing will be equal to 0. Okay. So we know, right? Equation A, that the parent function Okay, the parent function looks like this. Okay, d squared y over dx squared plus by a dy by dx plus by by is equal to 0. Okay. So we know, what we know is that if you look at the parent function, this term is equal to 0 because we don't have a dy by dx. Now, to solve the parent function d squared y or dx squared, we know that the roots, the roots are equal to minus a plus or minus a squared minus 4b divided by 2. Okay. Right? We know that. So let's look at the general. I know our a is equal to 0. I'm aware of that. Okay. But just let's for now assume that a is not equal to 0 for now. Okay. So I'm going to write out the general equation. Or the general solution is where y as a function of x, right? Remember, we are trying to determine the what? The onset on when deflection will occur. Okay. So this will be equal to e minus by ax over 2 bracket c1 sine bracket a squared minus 4b divided by 2x plus by c2 cos square root a squared minus 4b divided by 2, and then the whole thing x again. And then that is the general solution. So we also know for now a is equal to what? A is equal to 0, right? So y as a function of x now will be equal to e. Now we know a is equal to, so this is e to minus 0 bracket c1 sine square root of minus 4b over 2x, right? And then plus by c2 cos square root minus 4b over 2x. Okay. So for now, if I were to simplify further, we get this one will be equal to what? So e to the power 0 is equal to 1. So c1 sine, right? I'm going to take out the 4. So square root 4 take out. You have what? Minus b x plus by c2 cos cos minus b x also. Okay. So we know what is going on now is it's impossible to do minus b square root of negative. It's impossible to have a negative square root, negative within a square root. So that's where we know that this has complex conjugate roots now. So we know that this can be written as y x is equal to c1 sine b I x plus by c2 cos b I x. Okay. So note that p squared, okay, small p squared is equal to b. Okay. So therefore, so I'm going to call this equation b. Okay. So therefore,